Okay, thank you, everyone, and thank you, Chairman. Good afternoon, ladies and gentlemen. My name is Bushra Al Duri, and I'm a reader in chemical engineering at the University of Birmingham in the UK. Today, in the coming 20 minutes, I'm going to talk to you about supercritical water oxidation as a process for hazardous waste treatment and also for energy production. My talk will be actually an overview, so I will give a general background of the use of this technology, the definitions and properties of supercritical water, main applications of the technology, and a quick word about our research at Birmingham, and then the operational challenges and aspects of supercritical water oxidation and the commercial status of the process. Hazardous waste basically is actually the waste that is harmful to human, animal, and well-being of all plants as well. Hazardous waste is actually generated on site. It is generated on the premises, basically, of the modern industries like chemical, pharmaceutical, petrochemical, and also healthcare sectors. Now, the problem with this waste is especially organic waste, if it cannot be reused, recycled, or converted to anything or recovered, then it has to be destructed. Now, destruction of waste, if we have a quick look at the UK profile of waste production and generation, as we can see, there is various sectors, from household to commercial and industry, construction and others, and they have been increasing from 2010, 2012. By 2013 to 14, there is about 7.5 million tons of waste that have been actually dumped to landfill. And as we all know, the price of landfill is increasing, and then dumping stuff on the landfill means that some of it is contaminated, some of it is, all sorts of dangers, in addition to the fact that we're using lands. However, if we look below, on the diagram below, oh, here it is, yeah. And it's here. Here. Yeah. If we look at this diagram below, this is the landfill. The red is incineration, and the blue is recycle and reuse. Although over the years from 2000 up to 2014, we see that there is an increase in the reuse. However, there is also increase in incineration. So, as we can see from here in the 2000 to here, so this shows us, if we read it, about 8 million tons of hazardous waste has been incinerated in the year 2013-2014. Now, actually, if we look at waste hierarchy, the way we deal with it, the greens, either resource management, recovery, or disposal. This is the least favorite, and this is the most favorite. Of course, whether we adopt any of these approaches is not always up to us. It is very much dictated by the nature of the waste itself. So, as we can see here, landfill is the reddest. It means it's the worst. And then other disposal techniques, we'd rather prevent on the top, or reuse, or recycle, and so on. Now, landfill is at the bottom of the hierarchy. So it is the worst that we actually can do. Now, incineration, although incineration is the prevailing technique for the waste that actually cannot be recovered, cannot be reused. For example, medical waste, laboratory waste, healthcare waste, some heavy hydrocarbons that cannot be anaerobically digested or anything. So we do incineration, which is the prevailing technique. However, it suffers toxic emissions like NOx's, metal vapors, fly ash, in addition to the production of bottom products that are called ash, and they are put in the landfill. On top of that, it is highly energy intensive, because if the concentration is less than 40%, it has to be dried before it is incinerated. And that is why it is very highly energy intensive. And on top of that, there are growing directives against incineration and landfill, and these actually are the drivers for frontier technologies to replace landfill and incineration. On this word, we can say that supercritical water oxidation has the double advantage of replacing landfill and incineration. So what is this process? Supercritical water, very quick. I mean, I'm glad to hear the word supercritical before my presentation, because obviously another laboratory are working with supercritical technology, is actually water above its critical point. So looking at this phase diagram, the water above its critical point is called supercritical water. And it is generated by the raising the temperature and the pressure until we reach a stage that above the critical point, there is no distinguish between the liquid and the gas. Not only that, no matter how much pressure you apply on it, it does not condense. It keeps getting compressed and compressed and compressed. So now, what is special about it? If we look at the thermophysical properties of water, what happens is actually this area, the critical point, by the way, is 374 degrees centigrade and 221 bars, or 22.1 megapascals. So the density is greatly reduced, is the green line. The density, where is it? Oh, here. The density is greatly reduced. The Prandtl number is greatly reduced. However, the bulk fluid enthalpy is highly increased. Now, and the thermal conductivity, the most important thing about this diagram is actually the hydrogen bonds that characterize ambient water are hugely weakened and destroyed. And therefore, supercritical water does not give the physical properties of ambient water. What happens to it, it becomes completely miscible. In other words, produces perfect solution with hydrocarbons, polymers, as well as gases, because of the reduced hydrogen bonds and because of the lowered ionic product and conductivity. Thus, that means that it becomes a superior solvent for organic mediated reactions of polymers, hydrocarbons, biopolymers, and gas. In other words, if you put all these in one pot, you will actually have a homogeneous medium with very reduced mass transfer limitations and very enhanced diffusivity. And what you get is complete oxidation. Remember, if we put the organics with the oxidant, we have complete oxidation to CO2 with very, very little byproducts. And on top of that, significant energy is produced. Energy, actually, that is enough to preheat the system, and on top of that, to actually produce steam by heat exchange that is fit enough to produce electricity from steam turbines. So, a quick look at the application of the supercritical water technology. This is the same phase diagram as I put earlier. This is the critical point. This region, the subcritical region, can be used for hydrothermal reactions. If you like, the supercritical region can be used for oxidation and gasification. So the main relevant applications to what we're talking about today is the oxidation for the destruction of organic rich wastes with minimal solid residue and zero gas emissions. Also, gasification of organics, basically biomass, low-grade coals, petrochemical waste, to form hydrogen-rich combustible gas. The advantage of this to conventional gasification is actually it does not produce chars and tars. No polymerization in the middle, because it's a completely different chemistry of reaction. That's why. Subcritical degradation can lead to production of more useful compounds. You know, like breakdown of lignocelluloses compound biomass into more useful monomers, etc., HMF, to produce biofuels and other compounds from it. Now, I will take you into a quick overview of actually the theme of our work. I know the time is short, so I'm not going into results and technical. We can do that whenever you want to chat outside the talk. But the scope of our work is actually we investigate the enhancement of the supercritical water oxidation process of specifically nitrogen-containing hazardous wastes in catalytic-free systems using simple designed continuous reactors, i.e. plug flow. Now, what do we mean by enhancement? The process contains organics and oxidant under pressure. So what we have studied so far is the gradual feeding of oxidant. We do that in order to regulate the heat that is generated. Okay, we intend to do that. We have not done that because, well, we've done it in our laboratory and proved that it gives us even better conversion under the same conditions if we feed the oxidant little by little. Also, we tried the approach of adding alcohol as co-fuel. We used isopropyl alcohol to improve the conversion under more sort of mild, relatively mild conditions. And the aim is to maximize waste destruction towards benign, simple products for disposal or reuse of other applications. Now, the scope of our work, the compounds we worked with so far, just to show you, aliphatic nitrogen-containing compounds, aromatic and cyclic compounds, aromatic compound, cutting oil, and real waste. And the process has been done in a continuous plug flow reactor on a laboratory scale. The length is 12 meters, and the diameter is 1 millimeter internal diameter, 1/16 inch. We have done kinetic studies, conversion studies, all different studies. So this is our bend scale rig. We have, here is the oven, if you like. I worked in Japan for a year at the University of Tokyo where we used sand bath. But in my lab in Birmingham, we have an oven. This is the organic line. This is the oxidant line. They get preheated and then into a mixing point into the reaction. Now, this zone is the high pressure, high temperature. The temperature range goes up to 500 degrees compared to incineration, which takes place at 1086 degrees C. The pressure is 250 bars. So this is where it is. It is like a pressure cooking process. 250 bars, but a maximum of 550 degrees. This comes out supercritical, hot fluid, everything treated. This is the cooler where the heat is recovered. Now, because it is a laboratory scale, we do this in a simple heat exchanger and we use cooling water. But in industry, it's very important that you use recovery here. It's very, very important. And then this is where the pressure is relieved when the system goes into gas and liquid, clean water, and clean gases. So this is basically the process flow diagram of the supercritical water oxidation process. This is in the lab just to show you that actually we do it, because I'm not showing you any results, so I'm just showing you this is our lab. This is the oven. This is the cooler above it. The pumping materials, they go from this point here and go in and out again into this line. This is the back pressure regulator, the gas-liquid separator, and this goes to a gas flow meter, GC-TCD, to measure the gas flow rate, GCFID, and TOC to measure the liquid content. Now, from the lab to the real process, despite its attractive advantages, it has some challenges that actually have hindered its application since it actually was first, if you like, constructed or started in the early 80s, mid-70s to early 80s. I am going to touch on one aspect, specifically corrosion and salt precipitation, and talk about it a little bit and list the material of constructions that can deal with this process. Now, why does corrosion take place? Corrosion takes place due to the coexistence of oxygen, water at high temperature and pressure in the presence of heteroatoms, such as nitrogen, chlorine, sodium. These actually also some extreme pH values. Under this pressure and temperature, the other thing I said about water, it becomes completely soluble with all hydrocarbons. However, it becomes immiscible with salts. So if salts get produced, they come out in the supercritical environment. This causes plugging. Also, the metal of the reactor wall reacts to form an oxide on the wall. Now, this oxide is good to a certain extent because it makes a protective layer. But if it starts to dissolve and go away, it means the reactor is actually being eaten up. So all these have to be looked after. So if they dissolve, we have corrosion. This is just a quick picture. I'm sure every chemical engineer or chemist have seen a corroded unit before. So this is just a quick word on how actually can we prevent the corrosion. We can prevent the corrosion before it happens. In other words, we try to neutralize the acids. We try to get rid of the salts in using different reactor designs, or especially neutralize the acid by putting some base before actually the process begins. Now, look at the mechanism. We have the wall reactor. This is a diagram that I have drawn, so it's not something too fancy, but the wall, you get the oxide on the wall, and we call it the protective oxide. Now, it starts to dissolve. Now, the formation of the oxide and the dissolution of the oxide are very much a function of the properties of the water, the density and the dielectric constant. As we said, when we go from subcritical to supercritical, the density changes, the dielectric constant changes. So that will affect the corrosive behavior. What we need to do is actually to control the situation such that we have a temperature range and a dielectric range and a pH range that we are protected from corrosion. So this is essential that to get the temperature balance correct and to minimize corrosion. Now, materials of construction. As I told you, this is an overview. That is why I'm not going into huge details. We need materials of construction that resist corrosion, such as stainless steel. Between 300 and 500, and this temperature pH range, stainless steel is okay. However, if we have chlorine, if we have some compounds like this, titanium alloys are a better choice. Now, titanium alloys are very light. Although they resist corrosion, but they are actually light, mechanically weak. That is why they are used as a lining rather than a material of construction. Aluminium and silica-based ceramics, such as carbides, alumina and silicous carbides and nitrides, can be used. However, the pH cannot be too caustic. It has to be more on the acidic side. Nickel alloys, Hastelloy and Inconel are the most used alloys at the moment, and also new alloys are currently being developed. Now, commercial status. What is going on with the process at the moment? We have, this is a list. This is courtesy of Dr. Phil Maroney, who actually works in Psych, or it is Linton. Sorry, where it is? Here at the bottom. He was in Psych, and now he is in Lindus, is the process where he course. So this is his work, and he allowed me to show you this. The green technology, the green names processes, General Atomics, SRI, Hanwha, in USA, Mitsubishi, Japan, Korea, in Orlando, Superwater Solutions, Supercritical Fluid International in Ireland, and Inoviox in France. These are operating processes, plants. Now, if you look between the 80s and the 90s, a lot of processes started and stopped because of the corrosion. But since the middle of the noughties, 2005 and onwards, more research has been done, and the process is looking up now. So as we can see here, we have in total 5 plants. I don't know if I am pointing it wrong, or anyway. We have 5 pilot scales, 3 operational, 5 being built, 8 being done. So the good thing is actually the process has hit rock bottom, and now it is on its way up. So I hope I have given you a quick overview of the process and its potential, and commercialization is actually starting, and it's on its way forward. And there is, I think it has a lot of good applications, especially in petroleum and petrochemical engineering. I don't do research in petrochemical engineering, but I lecture in petrochemical engineering. My research basically in waste treatment, hazardous waste treatment, energy production, and my forthcoming project, all being well, fingers crossed, is actually energy from waste from supercritical water oxidation. This is a quick diagram of real waste treated on a bench scale unit in our school and in my lab. Within 17 seconds, it has gone from what you can see to clear water. So with this, I thank you for your attention, and I don't know if there is time for questions. If not, there is always other breaks, and I am here for the coming 2 days. Thank you very much.